Hi, everyone. Thanks for this great presentation. Saves me a lot of things I don't talk about. So I'm a big proponent of don't paralyze. You should try a lot of other things before you do that. And I want to give a comment to that. The data table folks, I think they're the only one presenting processing time benchmarks, but they also say how much would this cost if you run it in cloud. That's a really interesting thing, because if you run things a lot, it's going to get super expensive. And parallelization won't make it cheaper. It'll just be done sooner. And I don't know if anyone also made this, but I think it's like if you Google why is R the best language, someone said like each Google search will kill a tree in Amazon because you produce so much cloud compute. So one can think about CPU time, dollars, and even power consumption. So anyway, I'm not going to talk about that. I am going to talk about how you can parallelize things. I do want to thank the satRday organization, people that helped out with it. Thank Agro Paris for having this place. Our core, I always thank so much time in the silence for complaints about them. Fran, without Fran, we wouldn't be here today, I think. And also all the developers and users. So together we're doing this awesome thing called And I also want to say thanks to our consortium, because they got a grant to do a part of this. Okay, so why do we parallelize software? So the thing is to speed up the processing, and I'm going to say the wall time. We want to get it done today and not next week. There's also a reason like you can't actually do the thing in one computer. You need to distribute it to multiple computers, and they work in smaller parts. Sometimes it's too expensive to actually transfer the data. Ask people in astronomy, they can't send their raw data from the observatories. They have to compute there. And other reasons, like shiny. I'm going to talk about the first two, because they are definitely the easiest. And that's the one I'm addressing with future package. Although I have some ideas for the third one. So I want to give an introduction here. So hands up, who knows how to parallelize an R, or has run one thing? Like half. So I want to show you how, so I assume everyone knows about the L-apply. If you don't know, you can think about it as per map, I think. So imagine this case where we have a list with 4 elements, each of 50 values, and we want to calculate the sum of the 4 elements. And also imagine we have a very slow function. It's a toy example, but this is what you have to do. Assume that slow sum will now take 4 minutes to run these 4 elements. So one of the first things that came into R, so there was a package called multicore way back, but it was brought into R in 2011. MC L-apply means multicore L-apply. And for the computer scientist, this thing here is using forked processes, so you don't have to worry about variables and things, it just works. So here is how you would take that thing and run it in parallel on 4 cores, if you have 4 cores. That means it will be done by wall time in 1 minute. Okay? So this doesn't work in Windows. They made it so if you call it in Windows, it will fall back to regular L-apply. So if you want to do this in Windows, you do this approach. You can create a cluster of workers. What it actually does, it starts R in the background, like you would do it manually. And then you need to remember that that slow function, the slow sum function, now needs to be distributed to these 4 workers, because they're like pure vanilla. And then you call RLApply on the workers, the one you want to iterate, and this will take a minute. Things are sent back and forth here in the background. So you could do this manually, but this takes care of sending things. Okay. So stop, number 1. Please interrupt me whenever you want. If you want to ask a clarification question or type or whatever, please do that. So I want to stop already here to see if you have a question. You came to the right talk. Thank you for asking that. That's what I'm trying to solve here. So yeah, so the parallel package is part of core R, so anyone has this pre-installed, which is a nice thing. Yeah?
I also have a question.
Mm-hmm.
Do you copy the data?
So that the magic with the MCLapply fork processes, it's all taken care of by the operating system, Unix-like. That's why it doesn't exist. So it only copies if you have to, but R doesn't have to worry about that. That's why it always works. Like, you never run into like errors. So I want to say this. So as a developer, if you want to do parallel processing in your package or in your script, a script that you share with others, is like, which of these should I pick? And as you heard, there are like multiple alternatives. So that's one issue, you have to decide, and when you decide, you're stuck. What operating system will I be running on, or the users running on? Do I want to cover all operating systems, or should I just forget about Windows users? And then it's also this, oh, it worked on my computer, oh, I forgot to test it on this operating system, or that operating system. From a user perspective, you see the first one all the time on Stack Overflow. It's like, oh, I run this code, it doesn't work. And then someone said, oh, it worked for me. And then there's this long discussion, what's your session info, what version I run? Way back down there, so, oh, I run this in Windows, and the person trying to help is on Mac, and no one knows. So these things cost a lot of time. And also then there are people like, okay, I need more than my local computer. I want to run it in the cloud. So how do we support that? And if someone tried to attempt to support most people here, this is the code. You see it's quite a lot of functions. Like, I want to support the sequential, regular lapply, because I know that works. Then I want to support the Windows. I need to create it, I need to export things, and then fall back to MCLapply and others. That's just on the local computers. And if you want to add support to run on 2 computers in the same office, you need to add code for that. The cloud, on academic HPC cluster, another one. So this grows, and all you do is that simple lapply up. So it becomes very cluttered code, hard to maintain. Everyone invents their own version of this, and error-prone. Very hard to test. So a solution for this is to try to encapsulate these problems. And for each package, I think it came out on Run 10 years ago, or C-Run. One thing they did nicely is they separated the user, kind of say, I want to use this way of parallelizing. Here's a way to say, I want to use MCLapply, basically. And then the code is protected against that decision. The code looks like this. And that's nice. And then if a Windows user come around, they can do this. Linux users and Mac users can do this. If do this, and that's supported by another do package, which are the backends for each. So unfortunately, there are some, I wouldn't call them corner cases, but it's not perfectly cleaned up in for each. Can be done. So if you try this, you're going to get this. So if you tried various parallel processing, probably seen this. Oops, I didn't find that function. Because we do need to do this thing. We need to tell for each that this object needs to be exported. So for each is great. Didn't get all the way there, but it can. So the idea is to separate user decides on how to parallelize, developer what to parallelize. I think this is the slide I added to why the background of future. And I also want to communicate this because of I convince you that you can trust me. Now, I mean, so I have a computer science background, and then I did a PhD in mathematical statistics. I've always been applied. Since my first time I used R was 2000, fall 2000. I got involved in genomics projects early on. So various cancer research analysis, sequence analysis, microarray analysis, if you know this world. Large data, and always kept growing. So I always had to optimize things. And we developed methods, statistical methods that we shared with collaborators in labs. Some of these people had like compute clusters. They were very savvy computer users, Linux and Mac. Around at that time, I think. And then you had Windows users. I remember Children's Hospital in Melbourne, Australia, long hallway, all the way down. There was one poor person sitting on a Windows computer where everyone is running around trying to do this analysis. So me and my collaborator, we had to and we tried to support everyone. So that's where I'm coming from. And everything, then we try to like make it simpler for ourselves to code. So we layers and abstractions. And by 2015, to answer when I started Future, it's like, okay, all these different methods has something in common. So I decided to sit down and write it from scratch. And that brings us to the future. And like everything else in science, and someone else done this before. And it took me a long time to find it, but I was sure someone done it. Sure enough, in the middle 70s, a term called future. So this is hard to grasp in the beginning, but when you get it, it becomes But it might take an hour, it might take a minute, it might take half a year, but it took me 15 years. So future in programming terms, or mathematics, or functional languages, is an abstraction for value that will be available later in time. Don't know when, but it will be available. And the value is the result of an evaluated expression. And relate to that, or have an expression that has a value. And we don't really know what the state of the future is. It could be resolved and unresolved. Basically saying you don't have to know this until you ask. That brings me to, someone asked me, a gentleman asked me for years, I should put a cat here. Schrodinger's cat. Because it's kind of related, if you know Schrodinger's cat. It's like if you put the cat in with poison and things, quantum mechanics, unless you open the box, you don't really know if the cat is dead or alive. Future is a little bit like that. So, okay, what does it look like in code? So, if you think about this in standard R, you have an expression, you assign it to a variable. The expression could be 1 plus 2. A future looks like this. It's split up. Can people hear me, by the way? Or should I hold the mic? No, okay. We split up the right side that is calculated, evaluated, and where we assign it. We do that in two parts. So we say, let's create a future for this, and at some point in the future, later time, we are interested in the value. But by doing this separation, we can do a lot of cool things. So, well, this comes to this. I'm going to do two futures here. See if it works better here. So, loading my package, I haven't talked about that really. And my plan is to use the satRday people here to be my parallel backend. And I'm going to create two futures with two different calculations here. We'll get back to this later. Think about that, but I'll get back to you in a long time. Okay, so let's take another very simple example here. So we have this very slow function to calculate the sum of values 1 to 100. And if we do 1 plus 2 plus 3 plus 4, we get 5,050. We know this function is slow. It took 1 minute on 50 values, so it probably takes 2 minutes on 100. So if you have a problem that you can divide and conquer or split up, chunk it up so you can calculate in two parts, then you have the first step to parallel processing. So you can calculate the sum of 1 to 100 by first calculate 1 to 50. That will take us 1 minute, and then we can, we have to wait for this to be done, of course, after this. We can calculate 51 to 100, takes another minute. And then we can sum those up because the problem is such that we can bring it together and get the same result. So we didn't gain anything in time here, but we convinced ourselves that we can split it up, we can chunk it up in smaller parts. So with futures, we can do this. So we load a package, we say we want to do multi-process, this is your local computer. Depending on how many cores you have different number of workers that can work. Here, we create our first future, slow sum. This is like instant. And we get back to the prompt immediately. We can do the second future, and it's instant. So, and you don't really care how it's calculated, that's the definition of a future, and where. It's just going to be done when you ask for it, or that doesn't have to be done fast, but you can do other things here. We can like play around with our prompt, we can look at Twitter, we can do other things on the R. So, but then when we say, okay, now I'm ready to get the value, I ask for the value for the future. And if I do this after 50 seconds, it still has another 10 seconds to complete. They take a minute. So there it blocks and going to wait for 10 seconds. And then it's going to get the first part. And then probably the second one is done at the same time. And then we can add them up. See the idea here? We're only interested in values, so that's later in the code. Okay, so this is what I call the core basic functional explicit API, the two functions, future and value. In R, we can do infix operators, so we can actually abstract this away. So you can take that and make it into that. And so this is the same thing I just did with that syntax. So you see it's only those, what I call future assignment operators, that makes it run in parallel here. The only code change is to change those. Okay, so let's go back to this. What I gave out these two. First one. So what I could have done now, this is what I actually did before. I gave out two future expressions and I asked for the values. then I kept talking, so I'd never grabbed them. I could have gone and grabbed number 2 first. No point. So I got number 2, and if you haven't been ready, I had to wait for you to do the final math, and then you gave me the value. That was the first one, or the second one actually. And then I could do the first one calculated. And so that's what the future is about. Nothing really magic. I could send them by mail some across the world. We can actually do this in RT. We can send it across the world. Okay. And so the default is always to run sequentially. Design decision. It's not to burn up your computer by mistake, run something else at the same time. Multiprocess will work on all machines and parallelize on your cores. You can parallelize on multiple computers in the same office. I call them N1, N2. As long as you can do SSH into them, work, and it has R installed. You can also do it remotely, so I could connect to computers back at UCSF, California. But the key thing here is the code will still look the same. Okay, so now we come to the package itself. The idea is write once for the developer, run anywhere for the user. I tried to make it identify the minimal API that supports the most cases. 100% cross-platform, easy to install, 0.5 megabyte, and actually the biggest one is the digest package. I would claim it's very well tested, used in production all over. Lots of real CPU mileage. We get awesome feedback from users that find corner cases and things like that. And someone asked if it's production ready. I think it's safe. So the dependency is basically the API it provides are these functions we see plus a few more. That's the future package, and it depends on the built-in parallel, which in turn might depend on the old Snow, RMPI, and other historical packages. I also added globals package, which do analysis to find global variables, which uses the code tool package. So, but that's the basic framework. So again, why? And someone on Twitter said it's the interface of interfaces, and I like that. Explaining it. So it's trying to make everything look the same, so you don't have to worry about it. Fewer decisions to make. You don't have to pick a package. Use this style, then it should work everywhere for you. More power to the end users. It's also ready for the future. There might come other super cool parallel backends we don't know of, and they will just work better. So the user decides how to parallelize. Developers say what part of the code. And there are these atomic building blocks. I will come back to this soon. But it allows us to build much higher level frameworks for parallelization. And it has this automatic support. So future.caller package actually exists as the caller way of running things in the background. Batch tools is a compute cluster. We're working on a cluster MQ backend. Things can be just added, but they will just work in all cases. Okay, another thing I want to mention. Global variables is like very important, because if this future here is going to run on a computer in Australia, that computer in Australia has to know about a few things here if I run this. And the way we do this static code inspection, in an optimistic way, it works surprisingly well, covers most cases, which I was worried about it wouldn't. So basically the slow sum with the curly brackets there for the computer or abstract syntax, it looks like this. And you can walk that tree. And then you say, hey, there's a color bracket. No, that's part of the base R. I don't need to export that. Slow function or slow sum is a local thing. I need to export that. And of course, the data X needs to be sent. So this is done automatically or automagically. But it's magic that doesn't try to trick you. It's not a scam. But for people who don't like this or want to control it or make it more explicit in code, you can specify things you want to make sure. Okay. Any more questions? Okay, let's shortcut to my very second last slide. So for each Rick Callaway, he actually reached out to me. So this is last year. So they have a version on CRAN. So they do some very basic trying to find the globals, but it fails in several cases. So he reached out to me last year, and they have a version on their MRAN that tested a lot, which actually use future to find globals. So there is a plan to make for each work the same. We get the same errors. So they did 70%. Right? And the approach walking this makes 99%. Any more questions? Okay. So this is what I wanted to do in 2015. Like these basically three constructs here is what all the parallel backends have got in common. If you know the details of the MC apply, it actually has two things called MC parallel and MC collect. They very much could be called future and value. But then others don't have this. So my ideal dream is that all these interfaces that exist now, call them like this, then we could all plug into the same thing. But so the thing is, you can create a future, you can ask the value, and if the value is not done, you wait. But there are cases where you're like, okay, I don't want to get stuck there, I want to do something else. So there is that resolved function. You can say, hey, are you done? No, let's keep doing something else. Or you have multiple things. You go, are you done? Are you done? Are you done? And then the first one is done, we can start doing something. The resolved check is important. But with these components, you can do like so much. So here is your very first iteration, if you write this yourself, of lapply in parallel. Lapply takes a list of, let's say it's a list of elements, and then you want to call a function on that, and you pass ... that function. With the future constructs, building blocks, we just say lapply over those, but instead of actually calling the function, we create a future. This lapply we call internally will create a list of futures. Now, in the first part there, we distribute these jobs all over the workers we have. And then in the end, we say, give the values back. So that's, you can do that, and then there are other things, load balancing and random number generations I won't talk about. They're very important, but this is the key idea with this. Try this, you will work, you will give the same result, but in 1 minute. So there was an iteration, I did that as a proof of concept, and then more and more people asked for, let's do all the base functions. So did all the base functions. Instead of doing this now, if you want to speed things up, and just do this. It will work the same from your programming way of doing it. And then remember, the user will then say, hey, I want to parallelize in my computer or my cluster. And then another thing that people, of course, started to say, per. I did the same in per. I said, I don't have time, but please do it. So David, I actually don't know how to pronounce his last name. Davis, do you know? Okay, okay. Yeah. So he did the similar idea I showed you with how you build it from yourself. And he said instead of lapply, actually that should be map. Per map, you can do future map. And this runs in parallel. Same. But internally, these two packages are just base future, resolve and value, plus some bells and whistles. Okay. And then another thing, this was also, I did as a proof of concept. It convinced me it worked, and it's really simple. I can create a future backend for the for each package. So, super simple too. So I can say, register, do future, then run your regular for each. That before we could only do it on a local computer with a classical do MC and do parallel. But skipping ahead here, there's a batch tool package that allows you to do it on an academic HPC or scientific HPC. Sends it out there. So that means now, before they would do parallel, do MC, do Snow, do MPI, and a few others. I added do future, and so okay, what did that add to the community? It adds this community that whatever parallel backend that will be developed in the future, your for each code will automatically work on. So we have 1,400 packages in CRAN that uses for each or depends on it. Second level generation. So, for instance, the carrot package has for each internally. So this will now, this model fitting on carrot will now run on a compute cluster, which is not possible with other backends. And that was basically for free because of these three atomic building blocks. Okay, how much time do I have? Huh?
15 minutes.
Yeah?
15.
Okay, okay. So I will mention this. But I will. Maybe I should ask first. Who has access to an academic HPC cluster? 1, 2, 3. Okay, so there should. I'm going to show you. If you wouldn't know it, I would probably skip through. But so let's take a real example. What typical things I do once a month or in various projects. Genomic sequencing, human genome, 3 billion base pairs. You might get in one project, we get 8 individuals, like tumor studies, collect the DNA. I don't do that, people in the lab do that. We get the raw data, and one file, that can be like 50 gigs, 100 gigs patient. And the first thing we do there is this sequence data, when we measure this DNA, they're very short reads. We know the sequence on them, but we don't know where they are on the genome. That's called alignment or mapping. So you have the reference genome, we know that, and then we get all these millions and millions of reads. Okay, where should this fit? And you run along. That's where it's super important that the algorithms is clever, and that was developed in the 70s. How you do this in not the stupid way. Wait, instead of waiting 5 years, you can wait 1 minute. Then you do the second read and the fourth. But that takes a lot of time. So it takes maybe like 3 hours per individual to do this. So if you have 80 people, so they sit in files. They actually text files. So if we run this, align this, and this is an imaginary package function, but that's how it works. Do lapply on that. So that would take 10 days to run, sequentially. So you could do on your local computer now, use future L-apply. Say I have 12 cores, not on this, but another machine. Then we will cut this down to 20 hours. Our wall time got shortened, but there's still the same amount of CPU processing. Okay. But this is still not fast enough. And you can get bigger machines with more cores, but still not fast enough. So then we start using multiple machines. And what you see in a lot of departments, it's like, okay, we have several machines, and SSH into them, and I can run things, but there might be someone else running at the same time, so I log into another or two machines. That's a very common setup. So that works when a few people talk, but if people start running things at the same time, it falls apart. But you can do this with futures too, otherwise. If you have multiple computers yourself, you can do this. But when you grow, you start doing something called job schedulers. Any number of machines you can get, and there's submit to a queue, say I want this processed. Then when it becomes your time, many users doing stuff, then it will be processed and you get the results back. So there's no like stepping on each other's toes here. So, and this is what it actually looks like at the command line prompt. We write a bash script, few directives to the scheduler. This one said I need 12 gigabytes in order to process. Call the function, an executable HTTP line, pass the first argument, and then human reference genome. And then to actually submit this to the scheduler, you see qsub, this script, and then which sequence file patient I want to. So here I'm submitting two things, and there are lots of people in the world doing this, and then you go say, hey, where are my job in the queue? You say qstat, okay. One of my jobs started, the other one is still waiting to get time. All these other things are running. So now, thanks to the awesome batch tools package, they encapsulate this in R, so you can use R as the glue to create these things. So I built a shallow layer on top of batch tool called future batch tools that implements these very basic building blocks. So now I can do this. I guess I plan use the batch tool on the scheduler called SunGrid Engine. And when I do this in R, I can go look at the qstat and see it. Two of the, or I'm just looking at the first two here, 80 jobs running there. And that future L-apply now won't, the way future L-apply is, won't return until all the 100 jobs are done. There is, so let's forget about the HPC now, but there's another one related, cloud computing. So there's the, I think it's under our open side. Is that correct? Is this under our open side? No, it's not. No, that's the AWS one. Sorry. But so this package is like provides an interface how you can launch Google Cloud Compute instances, start them up using Docker, working on getting this under Rocker. Once have to see my name. So that, these first things, setting up instances, in this case 10 machines in Google. Then you just use the plan, use the cluster, and these workers. Then, in this basic example, simulating how to simulate pi, or calculate pi through resampling. This code makes actually things go out in the cloud and come back. Okay, wrapping up. So what I really want to see is like not just cloud compute, but other reasons to use future. I only been talking parallel stuff here, and that can use it for other purposes than parallelization. But we have the drape, which is an R. It's brilliant. It's like from Unix, it's like parse make. You just declare your different things you want to do, and then you say create everything, and it will figure out the dependencies and do it in the right order. They added a way of saying, okay, let's use futures to parallelize. There are other backends for them too. It's, and then there are nice ways. This is an old picture, but you can see how far it's gone as the process thing. I think that's a success story. Drake itself, regardless of future. Last year, Shiny said we can now use promises, and back end there is now future. So I know a lot of you came to the future package for Shiny. Okay. So many puns. So, you know how many I took away? No, but, so in my near future, so people have been asking for different things, but one thing I haven't mentioned is like if you have your expression or your function, it actually prints something. Depending where you ran it before, if you ran it in Australia, you wouldn't see that. But now that is actually captured, brought back with the value, and relayed on your local prompt. And that's same with warnings and messages. Also improved a little bit on the error reporting, so you can actually do some backtrace and trace back. People keep I mean, benchmarking that's more like, shouldn't be too hard to do. People asking about progress bars, number one thing. When is it done? When is it done? If you just want to do it on your local computer, it's easy. But we have to design it so it works the same everywhere. So when you write the code, it shouldn't break if someone runs on the computer. Be very careful of doing that, but it's happening. Killing future is one thing. If we get stuck, we can't do that right now. You just have to like ignore it or wait for it to run or you kill it. And related to that is like if there is something that fails. The computer you're running on had a power failure, then you can't get the value back. So that's starting fail futures. I want to mention future test. It's supported by the R consortium for run. The point with that is that every person who write a new backend, they had to like come up with their own test to make sure it worked. But now there will be like one future test package that validate all these backends that they work, so that those people don't have to depend on that. And also, you as user will know that all the backends that's claimed that they passed these tests, they will work. Trust is super important here. We don't want to have like random funny errors depending on where we run our program. And that's the for each thing asked about. Soon it's going to behave the same. Okay, almost done. In a very much bigger picture, there are lots of ideas going on here. One thing I want to do from day one, but I took shortcuts. Otherwise things doesn't happen. I want to make the concept in R of the future your container. Now I have a little bit, depending on the backend, different subclasses of backends that are knows about. So I want to separate backends perfectly from future. That allows us to do a lot. And then there are things like, I want to run this future on a machine that has a GPU, but if one of my workers doesn't have a GPU, run it locally. That's more like, how do we specify that so that works? Sure that this thing, I need a file in order to process this feature. If I send it to Australia, that file won't sit there. And then, just a very last example of futures can be used for other things. You can imagine someone actually sends you R code and data you don't trust. And you could, with the future, create a sandbox running in a Linux container and evaluate that thing, and we know that it won't hack our computer. All it will do is return a value. That's not parallel processing, but it's a sandbox processing. So, summary, unified API, portable code, You don't have to worry about much, I hope. Developer decides what to parallelize. User decides how. It's meant to be very simple. And if you try this, please don't worry about questions being stupid. There are no stupid questions. So please try it, and if you run into something, ask. And to people that will try to. Thank you very much.
Thank you, Henrik, for this great talk with technicalities that you try to make simpler, I think. So, thanks. Any question?
So basically, when you do the plan, the value it's enough to make cluster, for example.
Okay, let's take. Whoops. So you're saying it's similar to that. Similar to that. Let's find the one you're asking about. This one. Yeah. So it's it does that in the background. So the way that's a good point. But so basically, and actually learned something very important about this last week. Brian Ripley told me that bad things are done, and it's not my fault. But it took me 2 days to realize that. So the point here is like, when you create a set of workers in the background, and then you run your things, those workers will still be there. So you could choose to stop them as soon as you don't need them. In the future world, you can do that by changing plans. So if you go plan sequential, you could do that. Then it would stop whatever is there through garbage collection. I think, no, it would stop, but garbage collection will also take care of it. And the parallel package could do that also, but it's just not done. And about the Brian Ripley comment was actually, if you run code like this, if anyone is interested, if you run that thing, just the first workers parallel, make cluster, let's see, the last one here. If you run this and quit your R, it actually turns out, and I only learned 2 weeks ago, that there will be 4 R processes running. It's crazy, but there are hacks to detect that, but that's something that R needs to solve. But yeah, so anyway, that's very technical. Any more questions? So so there are 2 kinds of progress bars. That you can do it so when you do this map reduce, lapply, map, whatever, you split it up in like number of workers you have, 10 chunks, and you can send out those as futures, and then you can scan those. Are you done? Are you done? And then when you're done, although your future map function doesn't return, it can say increment by 1 for the progress bar. So future lapply could do that also. So
That's basically indicating the number of jobs that are.
yeah, exactly. Although each of those could take 2 hours to run. So some people ask, can I look into a specific future? How far have you gone? That's a much harder problem. So yeah.
Software doesn't show the amount of work done, it shows the number of
Futures, yeah. And so what I'm actually waiting for, and hopefully maybe someone else can do that here, create a very lightweight progress bar API that, because I don't want to depend on a particular, the favorite package of the day, but I think the progress bar packages could do something similar, like define 3 functions. They're very abstract, but yeah. Okay, sorry. Details again.
Okay. So thank you very much, Henrik, and Suzanne also for this session.